Okay, we are now going to solve some problems for the MHD equations. The first equation was, remember that we have introduced, was conservation of momentum. And this equation was given by Nm for one species, du over dt plus Nm number density times the mass, okay, u dot gradient, okay, space gradient of v is equal to n force, this Lorentz force, minus gradient. Actually, this is gradient of divergence of pressure tensor, which happens to give a vector, and plus collision terms. Okay, so this equation is the conservation of momentum, which we are solving now. First, we assume that no magnetic field, so these are assumptions. No magnetic field, so the only force is due to the electric field. So we have electric field in the system. So the Lorentz force is given by QE, and also P is scalar. As you remember, the pressure is a tensor, but we are assuming it's the scalar, and collision terms term is given as minus m and u, okay, nu, okay, this vector, by the way, and nu is the collision frequency. As you see, collision frequency means that it's 1 over seconds. The unit is 1 over seconds or hertz, but this is velocity. The velocity divided by time times nm, so it has the same magnitude as this term. So it's okay. So this collision frequency, and it's given in hertz. Okay. So this collision frequency for momentum transfer. We also consider steady state. Steady state means that d over dt terms are set to 0. So it means that nothing changes in time. So we solve this part only, no time-dependent part. Usually what happens is that if you solve something as a function of time, okay, say this is the just velocity, okay, one component of the velocity, so it will linearly start and then do something and finally reach to some value, maybe even go to 0. So now, as you see here, after this point on, it doesn't change, so that it's steady state case. So each quantity that you are solving finally, sooner or later, reach the steady state case in which the time rate is totally 0. It doesn't change in time. In this case, we are solving steady state, but the transient, so this part is the transient. Transients are just ignored, because for us, maybe this is more important. Usually, the transient part is very short, right? So the system goes to the equilibrium, which is the steady state case, in a very short amount of time, so that usually these transients are ignored, okay? For instance, if you have a circuit and have a switch, as soon as you turn the switch, the system goes to the steady state, depending on the values given. For instance, capacitor values, the resistors values, and all these other quantities that you have. Usually it's in the order of milliseconds or microseconds or something like that, very small amount of time. For us, most of the cases, the steady state is more important. That's why we can just ignore this term and try to solve this, which gives you steady state solution. Okay, so this is it. And also we say that velocities are very small. So this velocity is very small, so that the gradient of velocity is also small. So if it is small, so the change will also be small. So we just ignore this term also. So we ignore this term and that term. Now all we have is just these three terms. So that now if we write the pressure as a scalar, then 0 will be equal to, so this approximate equation, okay, n times q times, pardon çocuklar, şimdi bir telefon geldi. Alo. Allah Allah. Tekrar başlayalım. Bunu kapatalım.
Hocam tekrar başlamak için size bir şey soracağım o zaman.
Tabii sor. Bir saniye. Şunu ben... Ha, sor.
P ne oluyor?